Well, good day, ladies and gentlemen. This is the beginning of the 7th week of the Introduction to Quantitative Methods in Pharmacy. This week, we're going to expand upon the ideas that were started in the t-test last week in measuring the difference in mean scores. Well, in this case, we're going to talk about ANOVA, or the analysis of variance. At the end of this week, you should be able to, 1, understand the principles of dividing variation amongst the groups in ANOVA, and this is one of those situations where we're going to speak of it primarily at the theoretical level, but understanding the dividing of the variation is absolutely central to the concept of identifying why you are able to compare differences in mean scores. It seems kind of strange that you would try to identify differences amongst means by dividing it up into variation, but that is one of the key principles that we started with in the very first week about the idea of central tendency and variation around that mean. And in ANOVA, it just more directly looks at that concept. Secondly, you'll need to be able to distinguish an ANOVA, or an analysis of variance, between one variable, otherwise known as one-way analysis of variance, versus more than one variable, and the reason that multiple comparisons would be necessary. This, again, is an extension of the t-test, and we talked about multiple comparisons and experiment-wise there. And third, to discuss the concept of statistical interactions, to interpret the result of an ANOVA and explain it to a friend. And again, this is really what the key element of the course is, not so much to be able to calculate the analysis of variance, but to be able to take a look at a journal article that has used the analysis of variance to decide whether they have used it appropriately and to decide whether they have interpreted it correctly in the journal article. And then finally, to evaluate that journal article, evaluate the appropriateness of the display of the test result, and evaluate its interpretation. Again, the key thing here is, folks, is to make you discerning readers of the literature and to be able to evaluate whether someone has used a common statistical test appropriately and has interpreted it appropriately, so that you just don't automatically accept the conclusions of the authors. All right, we're going to use a couple of different scenarios, but this is the one that we will spend a lot of time on later on, and it illustrates a couple of those points that I want you to understand with the analysis of variance. So, in this particular study, it's being conducted with 2 drugs on the blood pressure of patients of different older age groups. So in this instance, a couple of the key points are that we're looking at 2 drugs. This is a categorical level of measurement, drug A versus drug B, and with different older age groups. So again, age groups. We're talking about groups of patients. Again, a categorical or at least ordinal data. The study is designed to ascertain the factor with the most impact on the blood pressure. So it's saying, given these 2 things, a patient's age and the drug, which one has the most impact on the blood pressure? Is it the taking of the drug or the age? Both of which we do know have an impact on blood pressure, but which has the most. And finally, the patient's systolic and diastolic pressures were measured at the start of the study, or the baseline, and at the end of the study. So again, much like the t-test and the chi-square test, what we're looking at in this instance is repeated measures on the same persons at multiple points in time on a variable, the blood pressure, which is numeric. So those are some of the key points to write down and to see how those are important in the use of the analysis of variance. A little bit ago, we used the t-test, and the t-test was very appropriate for using or for comparing the mean scores between 2 groups, but why is it inadequate with more than 2 groups? So let's take a look at the scenario that we talked about a little bit earlier, at least a piece of it. And we're reading a study on blood pressure reduction. And you have 2 drugs that are given to the patient with monotherapy, and two combinations, in other words, drug A plus the ACE inhibitor and drug B with the ACE inhibitor. So we really have, under this circumstance, 4 groups. Now, with those 4 groups, we have 6 tests of difference if each is to be compared to the other. Now, what ends up happening, however, and why it's inadequate, is that each time you do a single one of those 6 tests, you have no more information available to you than you would in a single test of any 2 groups. So you have 6 tests of 2 groups, but that is all that you have under each of those circumstances with each of those tests is the information about one group. You don't have any information with regard to all of those. In other words, is the monotherapy of drug 1 better than the monotherapy of drug 2? That's a piece of information. But how about the addition of the ACE inhibitor in each instance? We don't know overall then whether monotherapy or combination therapy is better. What we have then is, just like we talked about with the t-test, we have multiple comparisons, in this case 6 comparisons, but in doing so what we have done is increase the likelihood of experiment-wise error, or in other words alpha error or type 1 error, or of rejecting the null hypothesis when in fact the null hypothesis is true. So in this instance, you have 6 bits of information. At a 5% alpha error, we have a 30% chance of making an alpha error. In other words, rejecting the null hypothesis when it is true. Now, we also have, under this situation, 6 bits of information, but we have no single direct answer whether there is a differences of the 2 drugs and the combination. So while we know that monotherapy may be better of drug 1 or 2, we don't know whether monotherapy is better than combination therapy in these instances, or whether drug A or drug B alone or in combination is better. So this is one of the reasons why the t-test is inadequate with more than 2 groups, and why you have to look at another way of measuring the difference between the means. Now, there's a number of different concepts that you're going to have to review in getting prepared for a complete understanding of the analysis of variance. So first of all, as the name implies, analysis of variance, you have to understand variation. And in order to understand the concept of variation, go back and review the calculations of the sums of squares. We talked about variance and standard deviation. In other words, the variation around the mean. So for example, in a short review, basically what we are talking about is the difference between the group mean and the individual score squared. So that's what we mean by the sums of the squares. For each individual, the difference between their score and the mean score squared. With analysis of variance, we also need to think about, as we did with the t-test, is that what we're talking about here is the difference between 2 mean scores, the difference in depression scores between males and females, for example. But then we also need to think about the difference between more than 2 means. We have more than 2 groups, for example. We may have persons under the age of 65, persons between the age of 65 and 74, 75 to 84, and 85 years and higher. So we have more than 2 groups, then we may have the difference between more than 2 means. In addition, not only might we have 2 groups, or more than 2 groups within each variable, but we may have more than one variable. So we may have gender and age together, as we did in this scenario. We have to next review the concept of error, because again, what we're trying to do is to evaluate whether this difference in the 2 mean is a true difference, it is truly different from the population, or whether the difference that we might have found is really no different than a random sample from the sampling distribution of the population. In other words, there is no difference between the groups. The null hypothesis, there is no error. Next, we also have to look at the idea of independent samples, as we did with the t-test and the chi-square, looking at independent observations on different individuals versus looking at the same individual at two different points in time. With the chi-square, we had the Pearson's independent chi-square, and the dependent sample was the McNamara. With the t-test, we had the independent t-test, or the student's t-test, and with the dependent samples, we had the paired t-test. With analysis of variance, we'll have ANOVA and then repeated measures ANOVA, and we'll get to that near the end. And finally, just as we have had to with the chi-square and the t-test, we'll have to review the degrees of freedom, because the degrees of freedom are extremely important in choosing the critical value within the appropriate F distribution. So just as the t-test and the chi-square had different distributions depending upon the degrees of freedom, the F distribution, which is the distribution that is used in most of the general linear models, and we'll get more to that later on, which is both ANOVA and analysis of regression. They all depend upon the degrees of freedom. So you'll have to look at that concept again. All right. Now the first objective, one of the objectives that we had talked about, is how to explain to a colleague the sources of the variant in an analysis of variance. Okay, so this is the theoretical aspects that you need to understand before the mathematics begin to make some sense. Don't even think about the mathematics until you understand the logic of the analysis of variance theoretically. The analysis of variance is intended to evaluate the differences between means, but it actually uses variation to ascertain whether the differences are significant. So it seems kind of backwards that you would use differences in variance to evaluate whether the two mean scores are the same or different, but this is what most of the general linear models do. So the different sources of error are, first, the total error, the mean square error among groups, and so these are the key words in this instance, among groups, and then the mean square error within groups. So focus upon the key words among the groups and within the groups, because this is going to help you understand when we get to the global F test why the difference between those means or among those groups is considered to be significant or not. Okay, this particular slide conceptualizes the model of ANOVA that I was just talking about. And what I want you to do is to take a look at each of the different components of error within the conceptual model of the analysis of variance. If you look at Dr. Doug, the data dude down there, well, this is an absolutely essential concept for you to understand. If you do not take the time to understand this concept of the partitions of the different types of error, you just won't get it. All right, so let's take a look first of all at the total error. The total error then is the difference between each individual score, designated here by X, minus the the total sample average. So this is the average of all of the individuals in the study. So if you look at this, the difference between an individual's and the total, this is the total error. Now the within group error, what this means is that each individual score minus the mean score for the group average. The group average here. So this is an individual female score minus the score for the average of all of the females. This is an individual male score minus the average score for all of the males. So this is what we mean by within group error. Okay, this is what they would consider to be the mean squares error, and we'll get to that term in just a minute. This is the error amongst the groups. So what it does is it looks at the mean score of the group average subtracted from the mean score of the total sample average. This is where we look to find whether or not there is a treatment effect, is to look at the amount of error amongst the treatment group. The less error in this compared to the within group error, in other words, this proportion is higher, indicates that it is statistically significant. Now this J here, what the J means is for groups 1 to J of a particular variable. So for example, with females, with the gender variable, you would have two groups. You would have the male and the female. And so we then have the X of the individual male minus the male difference. Okay? So this is how it conceptually analysis of variance breaks out the variation so that you can determine whether there are differences in mean. So think about this conceptual model for a minute. What we're talking about is the total error is equal to the within group error plus the among group error. And this partitions out just like you would see in something like a Venn diagram. So again, let's look at it in a picturesque sort of a way. What we're talking about here is the total variance, or the sums of squares of the total, and it is depicted by this one large box here. Okay, now this total error then, as we showed you in the conceptual model, is broken up into two subcomponents. It's broken up into the variance within the group and the variance amongst the groups. Now, when we get to it a little bit later on, what we're going to be talking about are the main effects. This variance amongst the groups, if it is larger, means that the treatment has had more effect. The unexplained error is sort of the confusion, the things that are unexplainable. And when this is large compared to this, that means there is very little explained by the treatment. When this is larger, the treatment explains more. When this is larger, the treatment explains less, and error explains more. So let's take a look at this, for example, then. This has become a lot larger, thinking about this like a Venn diagram or something similar. So in this instance, the variance amongst the groups is larger compared to the variance within the groups. So amongst the total variation, this is like a zero sum. It does not change under this circumstance. The larger the proportion of the among variance explained by the effect, the larger the F ratio, and which is the ANOVA test statistic. So the more the variance is explained among the groups, the better. Well, let's take an example. We're going to take the one from the book, and it begins on page 164, where it says the intuitive overview of the analysis of variance. And what I've tried to do in the past few minutes is to give you a more in-depth explanation of the intuitive view. And in this particular example, it starts off with what they call one-way analysis of variance. Now, what do we mean by one way? It means that we're going to be looking at one variable. And so in this case, for example, we will be looking at the amount of free T4 as being the outcome measure, and whether a person is treated with hormone replacement or thyroid replacement or not. And so that's the one variable. Now later on, we'll get into situations in which there is a second variable added. So let's say gender. So you would look at both hormone replacement and gender, and then that's known as a two-way or more type of ANOVA. So the two-way is analogous. It is the theory or the way that you evaluate this analysis of variance is the same whether you have one or two groups, for the most part, theoretically. Mathematically it's different, but So we'll start off with the simplest case then in one-way analysis of variance. Now, one of the objectives was for you to recognize the full name for the acronym ANOVA. So it's analysis of variance, as I've said several times, so the A-N-O and the V-A of variant. Now we'll also, near the end of this time, get into one called ANCOVA, and this is short for analysis of covariance. And so we want you to recognize that as well. So let's begin by turning to the text. On page 167, what we're going to do is to go through the hypothesis testing step by step, the same as they do in the textbook. The data will be coming from page 166, table 7.2. So get this stuff together and be ready to refer to it, because we'll be going back and forth frequently between those. Okay, so first of all, just like most everything else, what we're going to be do in the first step is to formulate a specific hypothesis about the population parameter. And so if you go back and you think about that graphical representation that we had, where we had the population, the hypothesized population of drug D, and then we calculated the mean score, and we had the hypothesized population parameter for drug E and F. Well, this is basically, again, what we're trying to do here is to formulate the specific hypothesis then about this population parameter. So what is the hypothesis, or in other words, what is the clinical question? So the null hypothesis is that there is no difference in free T4 amongst the three conditions: the controls, the normals, and the persons on the hormone replacement therapy. Whoa! There's Dr. Doug the Data Dude. Well, I'll tell you, there's an important point here, and we'll get to it in just a second. And the alternative hypothesis is that there is a difference, so that the controls are not equal to the normals, or the controls are not equal to the persons on the therapy, or that the normals are not equal to the persons on the therapy. So in these three conditions, there is the potential for three different tests. Now, the reason that Dr. Doug the Data Dude is there is for the parts that are circled in the purple when it is circling the word or. With the analysis of variance, it is what they call an omnibus test. An omnibus, that's O-M-N-I-B-U-S. And what that means is that it tests whether there is a difference amongst one of those three different conditions. It does not tell you which specific condition will be statistically significant one from the other, but only that there is a statistically significant difference. And so in an analysis of variance, you first run the omnibus test. If it is not statistically significant, in other words, you accept the null hypothesis, then you are done. If you reject the null hypothesis and you accept the alternative hypothesis, then you do some post hoc comparisons, and we'll get to those in a few minutes. But the omnibus test tells you that there is a difference amongst the controls and the normals, or the controls and those patients on therapy, or those patients that are normal compared to those who are on therapy, but it does not tell you specifically which one of those three conditions is different. And that's what you need to make note of. And that's why Dr. Doug the Data Dude showed up, because this is a very important concept when it comes to the analysis of variance. So the clinical questions are the differences in the means, not statistically significant with regard to the controls, the normal, and those who are on therapy, or is there a difference amongst the controls, those that are normal, or those that are on therapy? So that is the hypothesis. The next thing that you need to do is step 2 is in the hypothesis testing process is to decide on an appropriate test, and in this instance, why is ANOVA an appropriate statistical test? So let's go to the flow chart, figure C2 in your textbook. It's appendix number C on page 400. Well, we're comparing differences between means, so why is analysis of variance appropriate versus looking at t-tests? Well, in this particular instance, the independent variable is categorical or ordinal, which is the same as you would see with the t-test, but under this circumstance, what you have is 3 or more groups within a variable. A t-test only allows you to directly compare 2 groups, so male and female, yes and no, and so forth. In this particular instance, you can then describe 3 or more groups, for example, drug A versus drug B versus drug C. The next question that you have to ask is, are you looking at independent groups? The analysis of variance, at least the one-way analysis of variance, asks you to look at independent groups. If the answer is no, and we'll get this to near the end, then we will use a repeated measures of analysis of variance. But we will spend most of our time today on the one-way analysis of variance and the 2 or more way analysis of variance. The next question that you have to ask is, are the data normally distributed? If the answer is yes, then you can continue on using the analysis of variance. If not, then there are some non-parametric techniques similar to chi-square that allow you to look at whether the groups are different. So in this particular case then, you have 3 groups or more that are independent. The outcome measures are normally distributed. The next thing that you have to look at is the number of factors. Now, this factors is what they term the different variables in analysis of variance. Variables and factors will be used interchangeably within the analysis of variance. Why? I don't know. I didn't make the rules up. The rules have been that way for 100 years, so we just got to live with them. So we're going to call them factors for this point in time. So do we have one factor or 2 or more factors? As I said earlier, if we have one factor, we have one-way analysis of variance. If we have 2 or more factors, we have 2 or more analysis of variance. So in this case, we have one factor, and that one factor is the drug, treatment or not. So we have our controls, the normals, and those patients who are on therapy, and that's why the one-way analysis of variance is appropriate. So in summary, the independent variable is at categorical or ordinal level of measurement. We look at the number of groups within each variable, and if we have 3 or more, we use analysis of variance. And with a t-test, we'd only have 2 variables. Well, in this case, then, we can have 3 or more variables. And the other thing, finally, that we are talking about in the dependent measurement is with analysis of variance, the dependent variable is at the continuous or numeric level of measurement. So the independent variable is at the ordinal or the categorical, and the outcome variable or the dependent variable is at the continuous level of measurement. That's absolutely essential that you understand that, and so that when you look at the literature, you're able to determine whether someone is using the analysis of variance correctly or not. Okay? The next thing that you do to select the level of significance, and again, the factor that you use in this instance is the amount of error that you're willing to accept. Again, historically, the probability value or the alpha error that is used in most of the scientific literature is 5 out of 100, that you would reject the null hypothesis and error. But in certain instances, in situations in which the correctness of the hypothesis is absolutely essential, sometimes you might use an error of less than 0.05, such as 0.01. The next thing in determining the critical value of the test statistic, so in addition to the error level that you determined in step number 4, that's the most important situation. The next one in the analysis of variance is the choice of the degrees of freedom. Just as it is with chi-square and the t-test, the degrees of freedom make a significant difference in the shape of the distribution. And the shape of the distribution then in the F ratio, or in the analysis of variance, the critical value that you will use to compare your obtained or calculated value against, depends upon the degrees of freedom. So in general, the F distribution looks something like this. And in the F distribution, most of the time we'll be worrying about what is happening in this right-hand tail. And with the F distribution, a 5% alpha error in this instance, then the critical value is around 3.88, somewhere in that instance, if you were looking at a situation where you have an infinite degrees of freedom. So just as the t distribution, the 5% critical value is much larger when you have fewer degrees of freedom. So in the F distribution. So in this instance, in most cases, we're going to be looking at an F value of approximately 3.88, and a 1% accepted error is 6.93. So these are a couple of values that you would want to keep available to you, the 3.88 and the 6.93. Okay, well, that pretty much does it for today. This lecture is a little shorter than the next one's going to be, but it's going to be about 40-45 minutes. So what we're going to do is we're going to do a summary to finish up what we talked about today. These are the important things for you to think about as you study for tests and assignments. First of all, when is the use of the analysis of variance appropriate when compared to the t-test? Most of the time it's appropriate when you have more than 2 groups. The t-test only allows you to use 2 groups for comparison. The analysis of variance also allows not only 2 groups within a single variable, but it allows more than one variable to be examined at the same time. The second thing that we talked about was the partitioning of the error in analysis of variance, or the partitioning of the variance, in order to show that the mean scores are different. And you do that by examining the total error, or the total sums of squares, the among group errors, or the between group error, which is the variance between the mean score of the group and the grand mean, and finally the error within each of the groups that you are comparing, which compares the individuals to that group. As a result, if you had no statistical significance, then the among groups error would be less than the within groups error. We talked about that in the case where we showed that if there was no variance, or the mean scores of all 3 of those drug groups that we looked at was the same, that there would be no variance. Therefore, the among group error would be 0 in the numerator, and therefore which it would be always less than the within groups. If there is statistical significance, then the among group error is larger than the within groups error, the mean squares error. When do we use analysis of variance? It's similar to what we talked about in the appropriate use of ANOVA, but what we wanted to get to finally was the fact that you use is the independent variables are categorical or ordinal data, and the dependent measure, or the outcome measure, is numeric data. The clinical question and the hypothesis that's being tested with analysis of variance is whether the means are equal, all of the means, or the alternative hypothesis is whether one of the means is different from all of the rest. So what we're trying to have you do here is to remember the idea that the analysis of variance is an omnibus test. It tells you that there is a difference, but it doesn't tell you where that difference is. Once you get a statistically significant result with the analysis of variance, then you have to do other analyses to find out which mean is different from another mean. And then the final thing that we talked about today was the idea of the F distribution, and mathematically how it is similar to the T distribution and how it varies with the number of people in the study. And then we talked about, just as you have with the T and the Z distribution, you have a critical value which you compare in order to determine your statistical significance. Well, now that I think about it, maybe we didn't talk about all of that stuff about the degrees of freedom, But we will talk about it next time, so that's something to look forward to, isn't it? So these are the things to keep in mind as we move forward to tomorrow. And what I'd like to do is to first of all to thank you, and second then to remind you to think about the things that might be causing you confusion amongst these 6 different areas, and send those to us and put them on the discussion board for a Muddiest Points lecture. So this is Dr. Doug, the Data Dude, signing off.